The second part of topic 13, or option B, deals with nuclear physics, and here we're going to talk a little bit about how we make some of the nuclear measurements that are made, specifically the nuclear radii and nuclear mass, and how we can measure the radius of different nuclei and the mass of different isotopes. Now, the radius of a nucleus can be measured based on scattering experiments similar to Rutherford's gold foil experiment. And using a few simple calculations, we can find what's called the distance of closest approach. So let's consider some alpha particle that has a +2 charge. It's an alpha particle, and it's shot head-on at some nucleus that has a charge of Z. Because the two both have positive charges, they're going to repel each other, and whatever velocity that we shoot it at, eventually that's going to slow down because of the repulsive force. And as we see over here, at some distance d, that velocity is going to reach 0. So it's only going to reach some distance from the center of the nucleus before the repulsive force has slowed it down so it has 0 velocity. And after that, it's then going to start traveling back in the opposite direction. Well, if our nucleus, our large nucleus, is stationary initially, then the total energy of the system consists of the kinetic energy of the alpha particle. So at first, all of the energy is the kinetic energy that's in this particle being shot. We're going to assume that the initial distance from which the alpha particle was shot is so large that there's really no potential energy based on the position of the two, and so the EP does not exist. At this distance d, the alpha particle is slowed down, come to a stop, and is about to return back the way that it came. At this point, all of the energy is electrical potential. So it's all potential energy that's stored in the position between these two particles. That potential energy is given by the equation K QQ over D. In this equation, K is a constant called the electrostatic constant. Q is the charge of the larger nucleus. Lowercase q is the charge of the particle, of the alpha particle, and D is the distance between them. Now, if we substitute in our charges, one of our Q's is 2e, and again, remember, E is just an electron. So, but here we're talking about a positive charge. Remember that protons and electrons have equal charges but opposite sizes, so we can still use E to represent the charge. So let's call, that's 2E and then ZE. So we plug those in there. We're going to keep using D, and so we get the potential energy is equal to K times 2 times Z, which is whatever the atomic number of the nucleus is, times E squared divided by D. That gives us the potential energy that's stored between the two, which, remember, is also equal to the initial kinetic energy of the alpha particle. So we use that idea of conservation of energy, and we can say that EK is equal to K times 2 times Z times E squared divided by D. Or if we rearrange it, we multiply both sides by D, divide both sides by the kinetic energy. We can get an expression to find that distance of closest approach. How close does the alpha particle get to the center of the nucleus based on the charge of the nucleus, or the atomic number of the nucleus, and the initial kinetic energy of the alpha particle. Now, if we use some numbers here, we assume that the initial kinetic energy of the alpha particle is about 2 mega electron volts, and we shoot it at a gold nucleus that has a Z, or an atomic number, of 79. That gives us, calculated through, a distance of closest approach of 1.1 times 10 to the negative 13th meters. So, pretty small number. This distance is outside the range of the nuclear force, which means that the particle is simply being repelled by the electrical force, the electrostatic force. So remember, our strong nuclear force acts only over very, very small distances, much smaller than that 10 to the negative 13th meters. So the only force that's being involved in this situation is that electrostatic force. Now if we increase the initial amount of kinetic energy, then the alpha particle is going to get closer and closer to the surface of the nucleus. And what we should see is that distance of closest approach gets smaller and smaller, but hopefully for obvious reasons it can't get any closer to the center of the nucleus than the order of magnitude that is the radius of the nucleus. And so by doing these experiments over and over, by increasing the amount of kinetic energy that those alpha particles start with, physicists have been able to estimate the radius of a nucleus. And they found that the radius, again, hopefully for obvious reasons, depends on the mass number, because the more protons and neutrons that the atom has, the bigger it's going to be, the larger the radius. So through that experimentation, they were able to determine that the mathematical relationship between the radius and the atomic mass of a nucleus was 1.2 times A, which is the atomic mass, or the number of protons plus the number of electrons, that atomic mass to the 1/3 times 10 to the negative 15th meters. And so this can give you the approximate radius of a nucleus with any given number of nucleons. So that's how we that's how we've calculated or experimentally found the radius. But now we also want to be able to look at the mass of a nucleus, not just the radius. So we're looking at all these different components of the nucleus, and the mass of, or the mass difference between isotopes of nuclei is measured using what we call a mass spectrometer. So let's look at how a mass spectrometer is used to find the mass of an ion. So we start with our ion source up here, and so we create a single beam of ionized nuclei that moves through this first slit S here, and this collimates the beam. And collimate just means to basically to focus the beam to get everything moving in the same direction. Once it gets through that, it passes through this field here where we have an electric field and we also have a magnetic field. This shading here is representing a magnetic field. And so the electric field and the magnetic field are at right angles to each other. And so as the positively charged nuclei move through the electrical and magnetic fields, they're pushed to the left by the electrical field, but they're pushed to the right by the magnetic field. And so the magnetic field and the electrical field are both acting on these charged particles, basically pushing them in opposite directions. And they have those set up to specific values so that they exert equal amounts of force in both directions and push the nuclei through undeflected. Now if the forces are the same, then EV, which is the electrostatic force, is equal to EVB, which is the magnetic force. And if we rearrange that, then we get the velocity, or V, is equal to the electric field over the magnetic field, or the electric field strength divided by the magnetic field strength. What that means then is only ions that have a specific velocity are going to actually make it through the second slit. And so we can kind of control what ions pass through. So the selected ions, the ones that we've picked, pass through that second slit, and once they get through that second slit, now they're in a second magnetic field. They're in a region with a second magnetic field, and it's just a magnetic field. And as we mentioned before, the magnetic field oriented in that particular direction pushes the positively charged particles to the right. And so it's going to exert a force to the right on those particles, which is going to cause them to curve. It's going to cause them to follow a circular path and actually end up going back the way that they came. The radius of that path is given by the equation we see here. R equals mv over EB. Here m is the mass, v is the speed, E is the charge, and B is the strength of the magnetic field. So you can see that the mass, if we assume that they're all coming through with the same velocity, the same speed, E here is the fundamental charge, the charge on an electron or a proton, so that's constant. The magnetic field is the same, so the only thing that's changing, or that could be changing between ions, is the mass. And so the only thing that's going to impact the radius of curvature is the mass. And so if we look at our diagram here, there are a couple of theoretical paths shown with different radii of curvature, and so they hit this photographic plate at different positions. Based on that equation, if we look at that equation, the larger masses are going to have larger curvatures or larger radii, and so the larger mass ions are going to be, or isotopes are going to be hitting farther out, and the smaller ones are going to have smaller radii. And this is essentially because that force that's being exerted is causing a larger acceleration or a larger change in direction on the smaller masses. And so based on the different positions at which those beams hit the photographic plate, or those isotopes hit the photographic plates, we can measure their different masses. And in this case, we see that based on the mass, the radii are different, but since we know the E, the magnetic field strength, the speed, and we're going to measure the radius, we can actually then calculate the mass based on those other four components. And so the mass of the particle is actually going to be equal to the radius times the fundamental charge times the magnitude of the magnetic field divided by the speed. And so here's how we would calculate the mass of a nucleus using a mass spectrometer. We know the magnetic field, we set that, we set the velocity, we know E, we measure the radius of curvature. All of that goes into calculating the mass.